So, in the last classes we have seen how biasing of the transistor is done, and we were considering different biasing schemes. Now, all these biasing schemes are basically for using the transistor as an amplifier for faithful amplification of an input signal. Now, we will be today discussing about the transistor being used as an amplifier, and to understand the operation of the transistor as an amplifier, we have to first understand the analysis of the BJT when a small signal is applied. So, small signal analysis of a BJT will be discussed today. Now, the small signal means the magnitude of the AC signal which is applied should be small enough to keep the transistor still in the active region of operation, because we want the transistor to operate in the active region. Only then the transistor will be able to faithfully amplify an AC input signal. Now, if the signal amplitude is very high, then it is seen that the transistor will be driven into either saturation or cutoff region, because when you have a very large signal at the input, then the base current signal will be having a high magnitude. So, peak to peak value of the base current will be high. In that case, if we look back into the transistor characteristics, input and output characteristics of the transistor we have discussed earlier. Again, let us recall that transistor characteristics. When the input biasing current is large enough, that is because of the application of a signal at the input which is having a high peak to peak value. Suppose this is the signal which is applied at the input of the transistor amplifier, then what will happen is that due to the application of this large signal, the biasing current in the transistor will be also high. So, the biasing current signal will be starting from the DC bias current, it will be going up and down. So, these values of the peak positive and peak negative of the small signal will be large enough. So, when we apply a large signal, then the biasing current IB will be also high, and if we start from say DC biasing current, then it will be also large. So, the maximum and minimum values of the biasing current in the transistor will be also high. Suppose this is IB 2, this is IB 1. So, these large signal of at the input of the transistor will again cause a large IC, because IC is equal to beta times of IB. So, if we now see the output characteristic, then this IC signal starting from the DC value of the collector current, which is because of the Q point, this current IC will also be large. So, if IC is so large that it enters into saturation, or IC is so large in the other half that it enters into the cutoff, then what will happen is that we will not be getting a reliable amplification, because if the transistor is overdriven, that is it is either entering into the saturation or the cutoff region, then one portion of the output signal which is VCE, that will be cut off. If it enters into saturation, this negative half will be one portion will be clipped off. If it enters into cut off, then the portion in the positive half will be cut off or it will be clipped. So, we will not be getting a faithful amplification, rather we will be getting a distorted signal. So, if we get a signal like this or we get a signal like this will not be desired. We do not want any distortion in the output signal, then what we are giving in the input signal. So, this is happening because the signal what we are applying is large enough to overdrive the transistor. The transistor is driven either into saturation region or into the cutoff region. In order that this does not happen, we must be careful enough to apply the signal at the input which should be small enough. So, if this small signal is applied at the input, then we can ensure that the transistor is in the active region of operation. That is what it should be for amplification. Now, when it is in the active region, the transistor is operating as a linear amplifier, because we know that in the active region the collector current relation with the base current is beta times of IB is the collector current, IC is equal to beta times IB, and when we consider only the signal, that is the AC quantities, this of course will be AC beta, but AC beta and DC beta does not have magnitude wise much difference. So, we can for all reasons which are valid, we can assume that the AC value and the DC value of beta are almost equal. Now, if beta times IB is equal to IC, that means it is a linear relationship, and when the transistor is linear, one advantage of analyzing the transistor in the linear region is that we can separate out the DC analysis and AC analysis, because when a system is linear, if we applied multiple signals to the system which is linear, then the total response of the system will be the superposition of the individual responses. That means, the superposition theorem holds when a system is linear, and that has advantage for analysis of the transistor. So, the superposition of the transistor means that the principle of superposition is held, means the response of the transistor amplifier excited by multiple independent sources is the sum of the responses of the circuit to each of the input signals alone. So, if we are having a DC voltage for biasing, if we recall earlier we were discussing the DC analysis, that was because we were concerned about the DC equivalent circuit, since we are concerned about the biasing schemes and the operating point. That is why DC equivalent circuit, when we considered, we were only discussing the DC condition. Now, when we are applying an AC signal for amplification, then we will be concerned about the signal analysis, that is the response of the BJT for an AC signal. And now, because this transistor is operating in the linear region, which is due to the fact that we are applying a signal which is small enough, which will ensure the transistor's operation in the linear region or active region, that is why we can now see that the total response of the transistor amplifier will be the summation of the responses due to DC plus and the AC. That means, DC response plus AC response can be now summed up to give the total response, and we can do the DC analysis and AC analysis separately, giving the corresponding voltages. Like DC voltage, when we apply, we will be having the DC equivalent circuit, and we can analyze the transistor under DC condition, and when we apply the AC signal, we will be considering the transistor in the AC condition. So, that is the advantage of this active active transistor, that active transistor being operating in the active region or linear region. That is what we are going to do. So, this condition is prevailing because the signal being applied is small, and we are having the linear relationship given by IC is equal to beta times IB. So, now in earlier discussions we held, we were discussing about the DC conditions and biasing. That was the DC analysis. Now, let us do the AC analysis of the BJT. What is happening when we are applying an AC signal at the input? What will be the output, and other relevant parameters we will be finding out considering the AC analysis. Now, in a transistor amplifier, because of the presence of DC and AC both, we are separating them out, we are separating the DC and AC analysis, and we are now concentrating on AC analysis. So, first of all, we must know how to draw the AC equivalent circuit for a transistor amplifier. So, that we will be discussing today. Now, AC analysis can be done if we first of all draw the AC equivalent circuit for the BJT amplifier. And for finding out the AC response of a BJT amplifier, first of all we must determine and draw what is the AC equivalent circuit. When I am saying AC equivalent circuit, I am meaning that I am forgetting for the time the DC part of the amplifier, and after drawing the AC equivalent circuit for the transistor amplifier, the transistor, which is the device and that is a semiconductor device, we must represent its electrical equivalent model, because as it is a semiconductor device, physically we know what a transistor is, but then in order to fit into the circuit analysis, we must draw the equivalent model of the transistor. So, the transistor is to be replaced by its equivalent model. Now, what a model is? Basically, a model is the combination of circuit elements properly chosen such that it best represents the actual behavior of a semiconductor device under specific operating conditions. That is, when we are considering a suppose common base or a common emitter transistor, then from the input and output characteristics which we know, we must model the transistor equivalently, which can be done by choosing the right parameters for expressing the behavior of the transistor under operating condition. That means, from the actual physical transistor, we must derive its model by properly combining the circuit elements, so that the behavior of the transistor, behavior means the input as well as output characteristic which we have studied, that can be reflected by that model. So, that means we have to first of all build the model for the transistor. If it is a common base transistor, equivalent model for that common base transistor has to be first of all derived, then we must fit that model for the transistor into the AC equivalent circuit. Now, if we consider a transistor amplifier practically, for example, we are considering a BJT common emitter transistor amplifier circuit, and it is an NPN transistor. Here the whole circuit for the amplifier is shown here. Now, as per our earlier knowledge, we know that these resistances R1, R2, RC, RE, they are in the biasing scheme, and we are applying a signal Vs, that is the applied source, which has to be amplified. That means, we must get at the output an amplified distortionless signal, and this resistance Rs, basically this is a series resistance which is present in a source in series with it, and it should be very small. Ideally it should be 0, but it is not true that it will be 0, because practically there is a small resistance in series with all the sources, that is denoted by this Rs. Now, we are now having 3 capacitances C1, C2 and C3 in the practical circuit. So, the purpose of incorporating these capacitances is that C1 and C2 are coupling capacitors. These capacitors are present to couple the signal, and this capacitance C3 is emitter bypass capacitor. The reason for applying C1 and C2, which are coupling capacitors, are that these coupling capacitors are used to pass the AC signal only and block the DC component. That is, basically a transistor amplifier may have a number of stages in cascade, that is in series we may be having a number of amplifiers, so that the final amplified signal should be large enough. So, instead of having only one BJT amplifier, we may be having a number of BJT amplifiers in series. Now, if that happens, suppose we have a number of stages coupled with this single stage, then we can very well see that the output at this stage, that means the amplified signal which we are having here, which is amplified version of this signal, this will be again fed back as input to the next stage. Now, when we apply this input signal, we expect that only the signal should be amplified. The DC voltage which is present in this circuit should not affect the input signal at the next stage, and that is ensured by the presence of this coupling capacitor, because this capacitor offer open circuit for DC. So, the DC voltages which are present in this first stage of the amplifier will not be affecting the next stage, and the signal at the input will be only AC, because this capacitor will prevent the DC voltage from interfering into the second stage input. That is why this capacitance is called coupling capacitors, because it is coupling the output from the first stage to the input to the next stage. Another purpose it is serving, this coupling capacitor which is present here, we can see, is that this DC voltage which is used for biasing, it should not reach the source Vs. That means we are interested in only amplifying this AC signal. Now, this voltage which is present for biasing only, it should not be coming into affecting this source. Meaning is that we need to amplify only this signal which is a small signal or AC signal Vs, and in no way it should be corrupted by this the DC signal, DC voltage, and that is ensured by this coupling capacitor, because this coupling capacitor is blocking the DC to reach this source. That is why we are applying a coupling capacitor here also. And moreover, this C3, which is an emitter bypass capacitor, it is called, this emitter bypass capacitor is the capacitor which bypasses the signal present here to pass through this capacitor, and it is bypassing this resistance, because we will be later observing this fact that because of the presence of this resistance Re, which is a part of the biasing scheme, the voltage gain of the amplifier is actually reduced. If the AC signal is present in this resistance Re, then the voltage gain will be reduced because of this drop, and that can be avoided if we connect a capacitor in parallel to this resistance Re, and this capacitor, if it is chosen properly having a high value of capacitance, then the reactance offered by this capacitance will be very, very small, as if it is short circuiting for the AC signal, and that is why the AC signal will be passed through this capacitance, it will be not going through this Re. That is, it is to avoid this Re for actually not reducing or for actually getting rid of that problem of reduction of the voltage gain, this capacitance, which is emitter bypass capacitor, is used. Now, while choosing the capacitance values C1, C2 and C3, we must be careful enough to choose a higher value for all these capacitances. That has a particular reason, because if the C1, C2, C3 capacitors are high, the capacitive reactance offered by this capacitance will be very small under AC condition. That is, the reactance offered by capacitance, we know it is 1 by 2 pi f c. Now, if this value is high, C is high, this is the reactance offered by capacitance. If this capacitance is high, under the frequency of operation where we are operating this signal Vs, that has a frequency, under that frequency of operation this value should be, the denominator value should be high enough, so that the overall quantity becomes very small, so that as if it is just like short circuit, almost like 0. If this quantity is very high in the denominator, the overall quantity will be very small, almost equal to 0. That means the C1, C2, C3, if they are very high, then the parts of this C1, C2, C3 capacitors will be like short circuit for AC. Under the AC operation, it will be like short circuit, and that is ensured by choosing a very high value, and under DC condition it is open circuit. So, this has to be remembered, only then we will be having the faithful amplification. And now, this overall circuit is having DC voltage as well as AC voltage both, and applying the linear condition of superposition, we will be now able to consider the whole circuit in DC and AC separately. DC analysis we have earlier done in biasing schemes that we discussed earlier. Now, under AC operation we will be focusing on the AC operation, and then the first and foremost thing is to do the equivalent circuit drawing for AC, that is AC equivalent circuit we have to draw for this. Now, in order to draw the AC equivalent circuit for this amplifier, first thing is that we must make all the DC sources 0, that is we have to short circuit the DC sources, because we are not interested in DC voltages, and this is only for biasing, and we are now concerned about amplification of the AC signal. So, we have to make the DC voltage 0. So, now VCC, which is the only DC voltage available here, it is to be made 0, or it is short circuited to ground. So, the AC equivalent circuit is drawn by first step setting all the DC sources to 0 and replacing them by a short circuit equivalent. Then next step is you replace all the capacitors by a short circuit equivalent, because we have chosen all the capacitance values quite high, so that for that frequency of operation of the AC signal it is like short circuit, because the 1 by 2 pi f c term will be very small, to be almost like 0, since the C value is very high. Then number 3 step is that to remove all the elements bypassed by the short circuit equivalents, which are introduced in step 1 and 2. While we have done step 1 and 2, then we got some short circuited paths. So, all the elements which are bypassed by the short circuited paths, those elements can be very conveniently now ignored or removed. That has to be done, and after doing these 3 steps, redrawing the network in a more convenient and logical form, so that the analysis will be conveniently done, we can now redraw the whole network after doing all these 1 and 2 and 3 steps. So, let us now see how to draw the equivalent AC circuit for this BJT amplifier. It is a common emitter amplifier employing the DC biasing potential divider bias scheme. So, following the steps, the first step is to make the DC sources 0. So, that is done by making VCC 0, or it is like short circuiting, means it is grounded. So, the ground potential is 0, that is done. So, if we just look into this point, it is having two resistances R1 and RC, both connected to VCC. Now, when we are making this VCC grounded, then these two resistances are also grounded. Just by showing this separately, we are just conveniently showing them that R1 is also grounded, RC is also grounded now. Then after this, we have to see the capacitances which are offering short circuit paths under AC. That is because we have chosen C1, C2, C3 to be large enough, and that has to be kept in mind. So, that is for designing this amplifier, we must pick up values of C1, C2 and C3 should be conveniently large enough. So, that this can be equivalently we can draw it like a short circuit. So, that is being done here. So, instead of this C1, C2, C3, we see that these are short circuited paths. C1 is short circuited path, C3 is short circuited, and this part is coupling capacitor is also having a short circuited path. So, now after doing these steps, now we can also notice here is that because of this short circuiting by this C3, RE is just removed totally, because the current will be short circuited, it will be going by this part, short circuited part, emitter current will be going by this part, it will not take this part of this resistance, because when it is offered a very easy part like having no resistance at all, short circuit, then obviously this resistance will be bypassed. So, that is why there is no purpose for this resistance to exist here, because this short circuiting part is there. So, that is why this RE is removed according to the step 3. Now, this is the equivalent circuit under AC. Now, we can do a step further and draw it more conveniently, because one point we are noting here is that this base is having R1 resistance to ground as well as R2 resistance to ground. So, it is like two resistances R1 R2 which are parallel from base to ground. So, now we can combine this R1 and R2 resistance, and instead of drawing separately, we can find out the equivalent of R1 and R2, which is a parallel combination of R1 and R2, and we can combine into a single resistance whose equivalent is R1 parallel R2, that is R1 into R2 by R1 plus R2. So, that is done next. So, here we just notice R1 and R2 both are parallel from base to ground. So, we are combining them R1 and R2 into an equivalent resistance R1 parallel R2. And also this RC, if we look back here, RC is grounded from this collector, but conveniently or most commonly it is not drawn upwards, this ground is always shown as downwards, and that is why conventionally we are drawing again by connecting this collector through resistance RC to ground, this point is ground. So, this is the conventional circuit which we have derived from the transistor amplifier and applicable under AC. So, AC equivalent circuit is this one. Now, after drawing this AC equivalent circuit, now we can go on to find out the required parameters like voltage gain, current gain, etc. for this particular amplifier, but then one obstacle is here itself existing because of this presence of this physical transistor. Now, as is shown here by this physical semiconductor device, as it is shown, which is a transistor, here it is of course common emitter, but this transistor, if it is kept like this, it will not be possible to analyze the circuit in terms of actual electrical engineering. That is why we have to replace this transistor also by its equivalent model. Equivalent model of this transistor can be found out or can be drawn if we again recall the input and output characteristics of a transistor. So, from the basic analysis of this behavior of this transistor or input and output characteristics of this transistor, we will be trying to find out the equivalent model for this transistor. So, that has to be done, only then we can fit in the transistor in its equivalent model into this circuit and then proceed for finding out the voltage gain, current gain of this amplifier and other related parameters. So, basically now at this point the whole amplifier after drawing the S equivalent circuit for will be looking like this. Basically this source and resistance are there, this point at this point is base, this point is emitter, we are taking common emitter transistor, this is collector, this is emitter. So, this type of circuits like a transistor are best expressed by two port system or two port network, means those systems which are having a pair of input circuit and a pair of output circuit terminals, like here it is shown. Suppose we are having this 1 dash as the input terminals, 2 dash as the output terminals. This is like two ports, input port and output port. So, there is a circuit in the input side, there is a circuit in the output side, and this system is called, this network is called basically two port network. For example, transistor as well as transformers are best expressed by this two port network, and in the transistor analysis also we will be following this. That is why I am introducing this two port network at this point. So, if we look into the whole circuit at this point, between these 2 points it is, this is the input port and this is the output port. Source and load will be external to this whole two port system. So, this input port is having all these parts along with the transistor, the circuit R1 parallel R2 and RC, this will be there. Only the source and the load are external to this two port network, and we can analyze the whole circuit in the light of this two port network, which we are going to do next. So, in this two port system there are quantities input voltage, input current, output voltage, output current, and conventionally the polarities and directions are showed like this. That is, upper point is positive with respect to the lower point of these voltages, and the currents are towards the system. I1 and I2 are conventionally shown towards the two port system. So, V1 I1, VI are the quantities of voltage and current at the input port, and V0 I0 are the quantities voltage and current at the output port. And from this knowledge of V I V0 I0, we can find out what is the input impedance. Input impedance means VI by II, that is equal to ZI, it is input impedance, that can be found out from this ratio. Similarly, at the output we can find out Z0 V0 by I0 is Z0 output impedance. We can find out voltage gain V0 by Vi, we can find out voltage gain, we can find out current gain, all these quantities which are very important for an amplifier, and these can be found out by considering the whole transistor amplifier as a two port system that we will be using. Now, still we are left with finding the model for this transistor. So, now in order to find out the transistor model, basically there are two approaches. One is the RE model, another is the hybrid model. These two models are used for equivalent models of a transistor. Now, we will be discussing RE model. RE means actually dynamic emitter resistance model, and this model has to be first of all derived for the different configurations of transistor we will be seeing. First of all, let us take for example a common base transistor. Now, common base transistor if we take, and we are considering say for example first of all PNP transistor, this is a PNP transistor. So, in the light of this two port network which we have just now seen, this is the input port emitter and base, this is the collector and base port is the output port. Now, the transistor is having input current IE and collector current IC is the output current, and this is the base current. This is a common base transistor. Now, in order to find out this common base transistor's equivalent model, we have to consider the emitter to base part of the transistor as a forward biased diode. It is nothing but a forward biased diode. Emitter base junction is forward biased in a transistor, collector base junction is reverse biased in a transistor. So, if we consider emitter to base this part, then this part is a forward biased diode, can be replaced or represented by a diode which is forward biased. So, this is a PNP transistor. So, obviously forward biasing means this P will be connected and N will be connected in this fashion. This is P, this is N, it is forward biased by this voltage. Emitter to base voltage is the input voltage, and the output side, if we consider the collector current, it is nothing but the alpha times of IE. This is like a current source. IC is equal to alpha times IE is a current source we are having at the output. So, it can be best represented by a dependent current source. This is the symbol for dependent current source. This dependent current source is nothing but alpha times IE, which is equal to IC, and the base current of course is there, which is IE minus IC, or IC can be written as alpha times of IE. So, it is nothing but 1 minus alpha times IE. This is the voltage, output voltage, and this circuit of course has one more thing which is not shown here, which should be a resistance at the collector. This resistance is R0. Because of this fact that the resistance in the output characteristics, if we just recall the resistance, output resistance of a common base transistor, it is almost infinity. Because of this horizontal curves in the output characteristic, even if you go on increasing the collector to base voltage, the current IC does not change. It is almost having horizontal shape. It is like this type of IC we were getting across VCE. So, basically this in the active region, this is almost horizontal, means the resistance in the output circuit is so high, it is almost like infinity. So, that even if you change this collector to emitter voltage, the current is not going to change, and that fact is the reason why we have not shown R0, or it is almost like infinity. This R0 value is infinity. So, it is well equivalent to not showing, because infinite resistance, if it is there is a part having infinite resistance, obviously there will not be any current flowing in that resistance. So, it is like open circuit. That is why very conveniently we can remove this R0, but exactly the whole circuit will be having this R0 also. So, now if we look into this forward bias diode, it is not right to keep it like this, because we have to find its equivalent and replace it by the relevant parameters. So, if we look into this forward bias diode and remember the input characteristic, then we can replace this this forward bias diode by a resistance, which is the dynamic resistance of the diode. Because if we consider the input characteristic of the diode, The input characteristic is a characteristic like this, that is input current input current is IE here versus the emitter to base voltage, that is what we are having in the input characteristic V, EB and IE. Now, this characteristic is forward bias diode characteristic. So, if a particular point of operation is considered, say Q point of operation, this is the DC biasing current. Now, around this point a small portion if we consider, then del V, this is del I. So, the del V by del I, that will be the dynamic resistance of this diode. So, this dynamic resistance can represent the forward bias diode, and that is what we are going to do. So, this characteristic, that is V, we are considering a common base. So, it is V E B. So, this should be V E B, emitter to base is common, input current is I E. So, this is the characteristic, diode characteristic between emitter and base junction. So, if we now consider the dynamic resistance, it can be found out around this operating point, that is the DC biasing point actually, that is the current which is flowing, the DC current is IE, and we are finding out this dynamic resistance by finding out the slope del VD by del ID, VD and ID, these are the diode voltages and currents. So, in order to find out the dynamic or AC resistance of this diode, we will be starting with the basic equation of the diode, ID is equal to Is into e to the power kVd by Tk minus 1. The symbols ID is diode current, Vd is voltage across the diode, Is the reverse saturation current, and K is 11600 by eta, eta being the value 1 or 2, and if we consider the higher region or active region, eta both for silicon and germanium can be, it will be only 1, value 1 for both germanium and silicon, and for the higher portion or active portion of the this linear region of the diode, eta value is 1. So, eta value will be considered as 1. Tk is the Kelvin temperature, centigrade plus 273. So, now if we now find out the derivative of this current with respect to voltage Vd, that is differential with respect to Vd of this quantity, will give us this Is is constant, reverse saturation current is constant, that is the leakage current. So, this is not going to change with Vd, that is a constant for this Vd. So, this Is will be coming out. So, this derivation, if I do this derivative, if we find out, K by Tk will come here and e to the power K by Tk into Vd will be left. So, now K by Tk into Is into this part. Now, if we consider this equation, we get that this e to the power kVd by Tk, this is nothing but Id plus Is. If we transfer this Is to the left, Id plus Is will be Is into e to the power kVd by Tk. So, this whole term Is into kVd by Tk can be represented by Id plus Is, and that is equal to, almost equal to, we can write K by Tk into Id, since Is is very small. So, as Is is very small, so we can approximately write this equation. Now, at room temperature, considering 25 degree centigrade room temperature, which is typically that is done in all these calculations. So, 25 plus 273 will be 298. The value of K by Tk then becomes 11600, because eta value is 1, K is 11600 by 298, it gives 38.93. So, now replacing this in the original equation, here did by dVd is equal to 38.93 into Id, that we are getting. but we want dVd by dId, which is the dynamic resistance. Dynamic resistance is actually dVd by dId. So, dVd by dId is equal to 1 by this whole term, and it after calculation 1 by 38.93 becomes 0.026. It is in volts. So, we can write it 26 millivolt by Id, and this 26 millivolt is called the thermal voltage Vt. So, basically we can write it as Vt by Id. So, this dynamic resistance of this forward bias diode is now 26 millivolt by Id. Now, if we consider the emitter base junction for our particular transistor, common base transistor, this Id will be nothing but capital I, capital E, that is the emitter current, which is the basically the diode current in the forward bias junction. So, we can now get from this was the circuit where we were having this between emitter and base, this was the diode. Now, if we replace it by the dynamic resistance of the emitter, we are having the circuit like this, that is this resistance Re, which is 26 millivolt by capital I, capital E, because the current which is the DC current, that current is capital I, capital E. So, this becomes 26 millivolt by IE becomes the dynamic resistance of the forward bias junction for the common base transistor. So, now if we again redraw the circuit, in place of this forward bias diode, we will be replacing it by this Re, and other part being the same. So, this is the Re model for the common base transistor. So, here the value of Re, dynamic resistance, we can calculate for a particular biasing point, what will be the DC current in the emitter IE. If we substitute in this term IE, then we get the value of Re, and that we will have to fit in. So, now we are having the equivalent model for the common base transistor. So, in the AC equivalent circuit, we can incorporate this model for the physical transistor, and we can proceed to find out the parameters like voltage gain, current gain, input resistance, output resistance, etc. for a common base transistor amplifier. Now, this example was for common base PNP transistor. Now, if we consider common base NPN model, it will be similar, only difference will be that the direction of this forward bias diode, since it is NPN, this is N, this is P, this is N. So, the diode will be forward bias from P to N. So, the direction will be like this, and the current directions will be also different, because now emitter current will be going out and base current and collector current will be coming into the transistor, and this current source will be current source direction will be this way, that is towards the transistor. So, this is the difference between the NPN and PNP, but it is the same model. So, now this is for common base transistor. Now, let us now see for common emitter transistor, what will be the equivalent model. Now, in a common emitter transistor Re model, if we want to draw, let us now for example start with an NPN transistor, and these small signals are represented by these small letters. So, IB is basically it is the signal component is shown, not the DC component, that is why small letters are being used to denote that this is the AC. So, if we consider common emitter, the emitter is common and grounded between the input and output circuits. So, base and emitter is the input circuit, collector and emitter is the output circuit, and the currents which are flowing for this NPN transistor, emitter current is I, which is coming out of the transistor, base current and collector current will be towards the transistor. Now, if we want to draw the model for this transistor, equivalent model, we can draw by considering the emitter base junction which is forward biased, and we are taking an NPN. So, this point is N, this is P, this is N. So, the diode which is in the forward bias condition will be from P to N. So, B to E will be having a forward biased diode, and the output circuit, if we now focus, that is the collector to emitter, basically we are having a current source in the collector which is nothing but beta times of IB. So, IC current can be expressed by beta times of IB, and so in the collector circuit, collector to emitter output circuit, there will be presence of a current source, dependent current source beta times of IB. But one thing to be noted here is the point of joining between the input and output circuits. In the earlier case, for common base transistor, if we notice, this point was grounded, which was common between input and output, but then here this point is connected. So, the current which is flowing through this diode is emitter current IE, this current is IB input current, this current is collector current, both are joining at this point. So, total current is IB plus IC is the emitter current. So, if we replace this forward bias junction by its equivalent resistance, like just we have done in common base, basically that is same. I mean, we can represent this forward bias diode by its equivalent dynamic resistance RE for this part, that is the emitter base junction part. So, we will be doing that, and this part, that is the current source, which will be the collector current now. It is current source because it is dependent on the base current by the factor beta. So, beta times of IB is equal to IC. So, now equivalently we can draw this circuit. So, this circuit will be having this resistance RE, and the current through this resistance is not IB, you have to mind it, this current is beta plus 1 IB, that is the emitter current, and these currents, input current is IB, output current is collector current, which is represented by this current source. Output side is having a current source, but then apart from this, again we have to note one fact is that the resistance between collector and emitter has to be incorporated, because this common emitter transistor does not have infinite output resistance, it is smaller than common base transistor because of the presence of a slope in the common emitter output characteristics. If we just remember the common emitter output characteristic, it was having a slope to the right. Because of the presence of this slope means there is a resistance which is not infinite, which is less than infinite. I mean that has to be incorporated to exactly represent this transistor in its equivalent model. So, R naught will be there. In fact, the value of R naught is in the order of mega ohm, but still to have exact representation of the common emitter transistor, we must have its presence here. That is why it is not ignored, since it is not infinity. But in common base we conveniently ignored it or just removed it, because it was almost infinity since the presence of horizontal curves, but it is not horizontal. That is why the slope has to be represented, that is represented by this output resistance. Of course, this value is high. So, now this circuit, so in fact we are having a resistance R naught is here also. Now, if I look into this resistance, the current flowing through this resistance is beta plus 1 IB. Now, in order to conveniently separate out the input and output circuits for further convenience in analysis, one trick we can do here is that we can represent this resistance by in another way, because if we consider the voltage drop between these 2 points B and E, what is this voltage drop? BE is equal to RE into IE, that is RE into beta plus 1 IB. So, if we keep IB and keep this together, what I get? RE into beta plus 1, but the current can be expressed by the same current IB flowing through this resistance, but the resistance value will be different now, it will be beta plus 1 into RE. This circuit and this circuit are not different, these are the same circuits, there is no ambiguity or any confusion between these two circuits, only conveniently it is drawn like this just for easy analysis, and actually the resistance RE is now reflected as beta plus 1 RE, but you see the current, this is the base current, is same current flowing in the resistance as well as the starting or the input current. So, this current IB it is flowing through this resistance meeting here with the current which is from the collector, this is beta times IB. So, IC plus this IB is now IE which is flowing to the ground. So, now flowing in the in this part. So, now at this point both IB plus IC are meeting. So, IB plus IC is here, and this is far better circuit than this, because our main problem was at this point these two are joining and this current is not IB, it is IE. So, it would have led to some difficulties in analysis. So, we have conveniently removed the difficulty by drawing the circuit in this fashion, and it will be now easy, because you can now notice that input and output circuits we are conveniently separating out. So, this is done by writing the equivalent or reflected resistance for this RE, which is nothing but beta plus 1 RE. So, now this circuit is the common emitter transistor equivalent circuit, which will be used in the AC equivalent circuit, and the further analysis will be now done for finding out the relevant parameters like input impedance, output impedance, voltage gain, current gain, all these will be found out. So, now this AC equivalent circuit, whatever we discussed in the beginning, this AC equivalent circuit will be having this transistor incorporated into it by this equivalent model. So, what we will be having, instead of this transistor's physical model or symbol, we will be incorporating that model which we have just now derived into the transistor, replacing this transistor by this equivalent model. So, if we now consider the whole circuit again, we can draw it by replacing this transistor. So, it will be now, if we have this transistor, like we are taking this common base transistor say. So, this transistor, and apart from this we are having the other things which will be there. I mean, for example, there will be biasing voltage, this is base, this is emitter, this is collector. So, there will be biasing voltage, there will be biasing resistances, etc. So, all these will be say there. Now, or some other things will be load resistance will be there, source will be there, all this will be there, but this resistance can be, this transistor can be equivalently represented by its model. So, it will be like this, it will be beta alpha times of IE. So, apart from this, this is your emitter current, this is the collector current, this is the base current, and other things will be AC equivalent circuit will be there. So, now from this circuit we have now conveniently represented this transistor which is replaced by this model. Actually, this part we have derived today. So, we will be now incorporating this in the whole circuit, find out the parameters of the overall amplifier, that we are going to do next. So, in today's discussion we have basically done the AC analysis starting from AC equivalent circuit, then finding out or deriving the model for the transistor, and our next job is to fit in the equivalent model for the transistor into the AC equivalent circuit and analyze the whole circuit in order to find out the relevant parameters for an amplifier, and these parameters are voltage gain, current gain, input impedance, output impedance, etc., which will be basically representing a transistor amplifier, BJT amplifier, and that we will be doing next.